So we're going to start by doing a problem. We're starting into integration, so we're sort of at our baby steps right now. We're just barely beginning, but that's okay. We can still ask questions and sometimes ask interesting questions. So we're given a lot of information. We're given 4 pieces of information about f of xy. Now we don't know what f of xy is. We just are given information about it. We're told the integral from 1 to 4, integral of 1 to 4, f of xy dx dy is 17. And integral 1 to 4, integral 1 to 2 of f of xy dx dy is 5. And integral 1 to 4, integral 1 to 2, f of xy dy dx is negative 3. Now if you weren't careful here, you might say, wait a second, hold on, wait, stop there. Aren't these the same integral? 1 to 4, 1 to 2? How are we getting different numbers? Yeah, they're not the same integral because the dx dy versus dy dx. This is why we talk about notation matters, because they represent different things, and we're going to go into what they actually represent. So if you hadn't written down what, whether it's dx dy or dy dx, you wouldn't know what that integral represented. So that's why we've been really after you. We really want you to get that notation down because we want to make sure you know what you're doing. And of course, the last piece of information here, the integral from 1 to 2, integral 1 to 2 of f of xy dy dx is 6. And we're asked to determine, if possible, the integral from 2 to 4, integral 2 to 4, f of xy dx dy. Now, I haven't actually done this problem, so that's why I put the words if possible, because I might get to the point like, oh, oops, can't do it. Not possible. But I'm optimistic. So I think a good way to start this problem is to think, okay, what do things represent? So in terms of the regions, because integrals have a couple of basic components, and one of them are the regions. And the regions you get from the bounds. So, for instance, the first integral says we integrate from 1 to 4 with respect to y, and 1 to 4 with respect to x. So I can come over here, and I can say, okay, 1 to 4, well, that's just a big rectangle. Actually, it's a big square. It looks like that. So 1 to 4, 1 to 4. So I have this big square, and the big square gives us 17. Okay, so I'll put 17 for the big one. It's the biggest one because you can see that all the bounds are smaller. Now the next one, 1 to 4, 1 to 2. Now that looks like I'm either going to have a horizontal one on the bottom or a vertical one on the side. Which one is it? Is it the horizontal one here? Again, I'm pointing to this second one. Is it the horizontal or is it vertical? Well, it's y is going from 1 to 4, and x is going from 1 to 2, so it's our vertical one at the start. So we have that this piece here, that part is worth 5, and I'll put a 5 here in that box. How about this, the next one here? 1 to 4, 1 to 2, f of xy dy dx. What is that one? Well, x goes 1 to 4, y goes 1 to 2, so that's the other one. That's the horizontal one. So you can see swapping the order makes a difference in our region. So this thing contributes to a total of negative 3. So in the whole purple, there's negative 3. And now, our last part, 1 to 2, 1 to 2. Well, that's that little square here in the corner, right there. And that's worth 6. So what I'm putting down is I'm saying, okay, what's the integral over these regions? And I'm just sort of drawing the region so I can understand how things start to interact with each other. The last thing to understand is, what are we after? Well, what we're after is we're after 2 to 4, 2 to 4, which happens to be this box. Now we kind of have a plan. It's like, okay, let's start to figure out pieces of information. For instance, I know that here, this box here, is worth 6, but this bigger box is worth -3. Now, what can I do with that? Well, what I can do is I can find what this is. So, this red one, what's the red one? And how do I find it? -9 is the correct answer. Why? Yeah, because you can think of it as, there's this nice fact that says if I'm integrating over two rectangles, and oftentimes we use this little u for two rectangles put together, of my function dA, then I can really think of it as just integrating over the two of them and adding them up. So this is if you know what's happening to your pieces, you can either separate and do the pieces individually, or you can put the pieces together. So we know that if I add the piece here, which is 6, plus whatever this part is, I'll get the whole thing, which is -3. So that has to be -9. How about this red part over here? Similarly, yeah, it would have to be -1. Because it's this piece plus this 6 has to give me 5. Now, how is this useful? Well, we can just now say, what do we have? We have that the whole rectangle, the big one, is a total of 17. And now I can think of it as 4 pieces. The part I don't know what that is, plus this little part, -9, this little square, 6, and this little part there, -1. Now we can rearrange. Well, of course, we can simplify first. -9 minus 1 is -10, plus 6 would give us -4. If we add 4 to both sides, we'll see that the integral we were after is worth 21. So this is using the notion that we can break things apart into regions, we can put our regions back together, and lo and behold, we can get our answer. All right, good. Of course, that's rectangles. But what if we don't have rectangles? What do? Well, the answer is we just do what we did before. We use the same idea. So there's a lot of information here, so we're going to take a minute to sort of digest. And we say, okay, well, what happens when we were doing rectangles? Well, when we were doing rectangles before, our basic philosophy was to say, let's slice things up. Look in each slice and add the slices up. We want to do the same thing even if our region that we're integrating over isn't a rectangle. So as an example here, you can see this part down here, this sort of green part, that's our region that we're integrating over. So this downstairs, this is what we would call R. There's our region. And you can see it's not a rectangle. It's got curves. Real regions have curves. Okay, but what can we do? Well, we do the same thing we did before. You can see here what we've done is we've done some slices. So we've sliced in one of two directions. And let's go through our two different types of slicing. What could happen? Well, if I'm doing the slice this way, so where you see is this blue piece right here, that blue piece corresponds to what? Well, remember we have our axes, x, y, and z. So as I'm slicing here, I'm going to be holding my x is fixed. So that's a fixed x, which translates into holding an x fixed. So notice here, I'm fixing x. So this is what I like to call slicing the region vertically. So when I'm talking about slicing the region vertically, I'm talking about a two-dimensional picture. So this is my x and my y. And I say, okay, well, what does a slice do? Well, a slice goes from your bottom curve to your top curve. So now if I want to understand what's happening, I can say, okay, I look in this slice, and the total is going to be the integral from one end to the other end, a to b, whatever the slice turns out to be, adding them up dx. So the slice, where do I go? Well, I start at the bottom curve, so I start at phi 1, and I go to the top curve. I end at phi 2 of f of xy dy. So you'll notice that this integral on the inside is going to produce something which is a function of x. And the function of x is going to show up in two ways. First off, it'll show up as possibly in the f of xy, but it could also show up because of the bounds. And that's perfectly fine. So what you can think about, one way to think about this process is that after you do the first integral, you started here with f of xy. By the time you finish this inner layer of integrating and evaluating, you're going to get down to only x. So you integrate out the y part. And now, after you have something which is only a function of x, you integrate that, and life is good. Of course, we can slice a different way. So the other slice, shown here in a somewhat orangish tone, I think that's an orange tone. What happened here? Well, here, this is where you had your y fixed. So you held y fixed. So if you come onto the picture of the domain, thinking this as x and y, if you're holding your y fixed, that's a slice that's horizontal. And so we're going from the left to the right. All right. So what happens? Well, the same idea. I'm going to start at the bottom, work my way to the top. So C up to D. And I'm going to say what happens in each slice, and what do the slices look like? Well, they look like integrals. From the left curve to the right curve are the bounds, f of xy dx. And as before, when we think of this inner integral, by the time we finish, it's going to be only a function of y, and then we can integrate with respect to y. Now, we want to get to the point where we're comfortable either going through either direction, horizontal slicing or vertical slicing. We want to be able to do both, because that makes us more dynamic. So one thing to remember is just keep in mind everything has an orientation. So we're really comfortable with saying, okay, we go from the bottom to the top. And our orientation is that the bottom is smaller and the top is larger. There's similarly an orientation when we go horizontal. So we go left to right. So left is smaller and right is larger. Just if you can always remember, smaller to large, then you'll be okay. Now, that's the idea for today. It says, hey, we can have more interesting regions. And so we're going to work through and do a lot of examples and try to understand what's going on. All right, any questions before we get going? All right, that's great. Let's go. See what we can do. Okay, so we start with an example. Find the integral from 0 to 1, integral x squared to square root of x squared plus y squared dy dx. So, what do we do? Well, let's just work through an integral that's been given to us. And here, we start by saying, okay, we start by integrating with respect to y. And we know we start by integrating with respect to y because of the dy. That says integrate first with respect to y. So what's the integral of x squared plus y squared with respect to y? X squared y plus 1/3 y cubed. Because at this stage, y is the part that varies, and x is the part that's constant. So that x squared is treated like a number. So if you integrate it, x squared with respect to y, it'd be x squared y. Now we're going to evaluate y equals x squared to y equals square root of x. All right? So we plug this in. So this is integral 0 to 1. I'll have plugging in square root of x squared times square root of x. What will that become? So you can add the powers. So x squared, square root of x is like x to the 1/2. So 2 plus a half is 5/2. Okay, so x to the 5/2 plus 1/3 square root of x cubed, which we can write as x to the 3/2. Good. All right, now we're going to subtract, plug in x squared. X squared times x squared, x to the 4th, and plus 1/3 x squared cubed, x to the 6th. Now, on a side note, notice my parenthesization game is spot on, because a lot of people will forget to put parentheses here. And they'll say, oh yeah, the minus x to the 4th, and because they forget the parentheses, they'll add that 1/3 x to the 6th. Don't make that mistake. Be careful. Use parentheses. Parentheses save points, and all points are important. So if you were to simplify this, which you really can't really do much, but at least we can distribute that minus through. So minus x to the 4th minus 1/3 x to the 6th. Okay, let's integrate. Well, integral of x to the 5/2. It'll be x to what power? 7/2. And then times in front by 2/7. Okay. Be next one, x to what power? 5/2. Multiply in front by 2/15. Because we already have a 1/3, then we're going to add another 2/5. A third times a 2/5 gives us 2/15. Okay, the next term, x to the 5th multiplied by 1/5. Okay, last term, x to the 7 multiplied by 1/21, because we already have a third, and then we're going to multiply by another 7th. And this is going to be evaluated from x equals 0 to x equals 1. The nice thing is when you plug in 0, you get 0. So you plug in 1, and you get, okay, this is 2/7 plus 2/15 minus 1/5 minus 1/21, which, of course, would be perfectly okay if we were on a test. But we're not in a test. We should keep going. All right, if we wanted to finish this, what would we do next? Common denominator. Common denominator of 7, 15, 5, and 21? 105. Okay, which is 3 times 5 times 7. So, if I multiply 15 times 7, that's 105. So the first term will give me 30. If I multiply 15 times 7, that sounds familiar, that's 105. So the next term will be plus 14. If I multiply 5 by 21, that's 105. So this will be minus 21. If I multiply 21 by 5, that's 105. So that'll be minus 5. So we get 44 and subtract 26. 44 subtract 26 would be 18. Now, do 18 and 105 have anything in common? They're both divisible by 3. So I can take out 6. And then if I divide by 3, that's 35. 6 over 35. Okay, there you go. Now you might say, what is that? And the answer is it's 6 over 35. I mean, we haven't gotten to the point of saying, what does the integral represent? First, we're trying to say, okay, let's develop the tools to help us get to the answer, but we'll soon develop questions that we can actually answer. All right. Now, notation is really important. And so I keep saying notation is important. The reason notation is very important here is that when we look at these bounds, bounds are really just ways to describe the region. And so we want to be very, very careful when we're working with the bounds. So as before, we have that the inside integral goes with the inside variable, and the outside integral goes with the outside variable. So that when we're reading this, we can say, okay, what this means here is this outside integral goes with the x. So when I see a to b, that really tells me that x is going between a and b. So x goes from a to b. And the next layer says y, it goes from phi1x to phi2x, which tells me that it's really corresponds to the inequality phi1 of x is less than or equal to y is less than or equal to phi2 of x. So you can take an integral that's given to you, and you can actually figure out what's the region I'm integrating over by looking at the bounds. So even if they didn't say what the bounds were or what the picture is, we can figure that out. And so one of the things you can get into the habit of, you don't have to do this, write this down, but you should always think of whenever I have bounds, I have, x equals a to x equals b, y equals phi1, y equals phi2. There's this sort of hidden y equals and x equals that's going on. So let's actually test this idea. So I claim that if I have the bounds of the integral, I can sketch the region that I'm integrating. So let's look at our integral that we just did. So we went from 0 to 1. What does that tell me? X goes from 0 to 1. Now, x squared to square root of x. What is this integral telling me? So x squared is less than or equal to y, less than or equal to square root of x. So these integrals here are giving me my region described in terms of inequalities. Now we want to sketch the region. So we say, okay, draw some axes here. So we have y equals x squared. So when we're drawing the region, we want to look at the curves. So the curves are the inner integrals. So we have y equals x squared. So maybe this is y equals x squared. And it can continue over there. Y equals square root of x is there. Now, I can't quite fill my region in because I haven't figured out where my x goes between. But let's do that. We start at x equals 0, and then we go to x equals 1. Now, it turns out, 1 could be there. It could be over here. But in fact, 1 is a very special point. It's where they cross. So that's 1. Now, it doesn't have to be, but in this case, it is. So what's happening is x is going from 0 to 1. And then if I fix any particular x value, I would say, let's say I fix the x value here, then that y is going to run up and down between these curves. So that what we're really doing here is this is a case where we're slicing vertically. So as we move along, we're slicing our region up in this fashion here to get our answer. And so our region is this something, it looks kind of like an eye, maybe. But that's our region. Okay. Well, let's try a little bit more. So let's sketch the regions which are associated with the following integrals. So I have two different integrals here, and we'll just need some practice. So let's start by writing down the inequalities for the first one. What does this tell me? The outer layer. What does the outer layer tell me? X goes from 0 to 2. Now we go to our inner layer. What does that layer tell me? Yeah, so the fact that it's a dy tells me I'm trying to tell you something about y, and then I'm going from 0 to x squared. 0 to x squared. So we come over here and we sketch. So we've sketched our curves. The curves are the second layer, or I should say the innermost layer. So y equals 0, that's an easy function to sketch. That's just the x-axis. Y equals x squared, that's also easy to sketch, something that we've hopefully learned to sketch. That's simply the parabola. And now we say, well, we go from 0 out to 2. So maybe that's 2. Okay. And this is a case where for a particular x, we're running up and down. So we're slicing this region in a nice vertical fashion, and our region is this whole part right here. All right. Yes? Right? Good? Okay. All right. Well, let's try the other one. Okay, let's look at the outer layer. What is the outer layer telling me? It's telling us about y. Because again, remember that these hook up. So we know that 0 is less than or equal to y, is less than or equal to 4. What is the inner layer telling me?
X is greater than y.
It's about the x, and it's between root y, square root of y, and 2. All right, so now we sketch the curves. Of course, it's going to be a little bit more interesting because we're very used to sketching the curves of the form y equals something of x. We're a little bit less familiar with x equals something of y, but hopefully these aren't too bad. So x equals square root of y. Now y equals square root of x, we know that shape, it would look something like this. X equals square root of y, well, it essentially turns it sideways. It flips it. And so x equals square root of y would look something like that curve. So this is x equals square root of y. X equals 2, well, that's not so hard. That's just this line, x equals 2. All right? So we have x equals square root of y and x equals 2. And now what happens? Well, if I look at a particular y value, so say I'm here, I say, where do I start? Well, I start at the square root of y, and I run over to 2. So what's happening is that whatever this region is, I'm slicing it in a nice horizontal way. So where my x is running between these two curves. Okay, so my region would be this one right here. Now, let's pause for a second and look at these two. What seems to be the case? Turns out, and I didn't mark where 4 is. 4 is here. They're actually the same region. What does that say about these two integrals? They're equal. They're actually representing the same thing. So what we've done is we said, look, there's different ways to describe the region. And so the two integrals will be the same. Now, it's not totally obvious that they're the same. And notice it's a lot more subtle than what we had before. See, previously, when we had just like A to B and C to D, it's like, oh, it's really easy to swap the bounds. You can see that doesn't happen here. It's not just a matter of like, oh, woohoo, I just swapped them easy peasy. No, no. Life isn't easy anymore. You've got to work a little bit, but not too bad. So one of the ideas we want to be comfortable with, and this is a big idea which is 100% going to show up on exams. So you really want to make sure you know this one, is the idea of changing the order of integration. But really what it comes down to when we talk about changing the order of integration is really understanding how do we describe our region. Because that's what happens. So we want to go from some integral, say where we're integrating dy dx, to some other integral where we're integrating dx dy. Again, it's not as simple as just switching. So what's the process? Well, the process is not so bad. You start by, what are your current bounds? And how do we get those? And the answer is, whatever is given to us, that stores what our current bounds are. So we can read off our current bounds from the current integral. As we did in these problems, we say, okay, the outer layer tells us where the outside variable goes between, the inner layer tells us what the inside variable goes between. And there's a comment here, which I think, it's a really nice comment down here. I just want to point this out. If you look on the bounds on the outer integral, it should always be between two numbers. So the outermost integral should always go from a number to a number. The next layer in is always going to be between two curves. So you'll see like, y equals 0 to y equals x squared, or x equals square root of y to x equals 2. So the outer layer numbers, the next layer is curves. Now, spoiler alert, we're going to go and do integrals with another layer. What would the next layer be? Can you think about what it would be next? Well, numbers, curves, surfaces. You're probably thinking, ooh, what would the next layer be? We won't do that. But it would be hypersurfaces, probably is what we'd call it. Okay, so figure out what the current bounds are. Once you have the bounds, draw the region. And I like to also draw how I'm currently slicing the region, just to understand what's happening. So we did that. We took our bounds and we drew a region. And now label all the curves. So we can do that. So for instance, if we came here, there's actually 3 curves that are bounding this region. One of them is very easy to label, this bottom curve, y equals 0. The other one is also very easy to label, x equals 2. The last curve, it has 2 different representations because you want to write both as x as a function of y and y as a function of x. So this last curve would be y equals x squared if I wanted to write y as a function of x, or x equals square root of y. And it's that ability to switch the description that helps us convert from one to the other. And now, the last part is use the pitch to determine how do you break this into parts. You might need to. It might be that if you integrate with respect to x first and y, you need 1 integral, but if you do y then x, you might need 5. Or vice versa. So you might have to break things into parts. For each part, figure out what the bounds are and work the picture. Now, there's a comment here that says, recommend working from the outside in. Now this says, what does that mean? Well, that says, set your inner bounds first. That's just a personal preference. Oh, sorry, not inner bounds. Set your outer bounds. There we go. Outside in, not inside out. You want to integrate from the inside to the outside. When it comes to setting bounds, I find it easier to go from the outside to the inside. All right. So that's the idea. And let's do some examples. Any questions about the process? All right. It's not so bad once you sort of get the flow of it. Figure out what the current region is, and then say, okay, how can I rewrite it in the other way? So, change the order of integration for the following integral. Integral from -1 to 0. Integral from negative square root of y plus 1 to square root of y plus 1, f of xy dx dy. So we'll work the process. So the first thing is, we've got to figure out our bounds. So what does the outer layer tell us? Well, so the outer layer is with y. So -1 is less than or equal to y is less than or equal to 0. What does the inner layer tell us? Negative square root of y plus 1 is less than or equal to x is less than or equal to square root of y plus 1. Okay. Well, let's sketch our picture. We're going to be mostly negative. All right. So let's think about the curves. How about we think about this curve, x equals square root of y plus 1. Now, we actually drew x equals square root of y a few minutes ago, and it had this shape. It was like almost like a parabola. What happens when we add that plus 1? What does that do? Shifts it what way? So currently, square root of y looks like this. Do I shift to the right? Do I shift to the left? Do I shift down? Or do I shift up? I'm going to shift down. So let's say this is at negative 1. So this is x equals the square root of y plus 1. Now, I will admit it's not so obvious, partially because the plus 1 is on the inside. So when I have the plus 1, I have to think about what is that doing. And oftentimes it does sort of the opposite of what you think. And so you can think about when you have y equals square root of x plus 1, what would happen to that? Well, you think, oh, the plus 1 would shift it to the right, but actually it shifts it to the left. So instead of shifting it up, it shifts down. One way to convince yourself that this is correct is just think about, okay, where should I start being? Where does the domain start? In other words, when does square root of y plus 1 even exist? For which values of y? Yeah, starting at negative 1. Negative 1 is the first time I'd have a value. And so if I plug in negative 1, I'd have a value for x equals 0. So that tells me that negative 1 here at 0 comma minus 1 is a point on the curve. So that helps me figure out where I should go. Now where does x equals negative square root of y plus 1 go? Or what does it look like? It's the same thing but flipped across. So this is the curve x equals negative square root of y plus 1. And now we can start to see where we're going. It's like, oh, negative 1 is the very bottom. This is y equals negative 1 is down here. Y equals 0 is up here. So what's happening is we're slicing between these two curves. So our region is this sort of bottom part. It's a bowl shape. So that's our region that we're integrating over. All right, so now we understand at least what our region is. Let's talk about our curves. Now, some curves to bound are pretty simple. How about this curve? That bounds our region. What's the formula for this curve? Y equals 0. All right. Now, over here, we already have the formula x equals square root of y plus 1. If we solve for y, what would we get? X squared equals y plus 1, or y equals x squared minus 1. So this curve, I can write as y equals x squared minus 1. How about this curve over here? Well, square both sides, x squared equals y plus 1, or y equals x squared minus 1. It's actually the same curve. Ooh, nice. Nice, I like that. Okay, so now we've gotten our picture, we've labeled our curves, and we're ready to figure out our new bounds. So we're going to be slicing now vertically. And what I like to look for is I just sort of check, am I always consistently having the same function on the top and the bottom? If I ever switch, then I have to break up my integral. In this case, we always consistently have the same functions. On the top, what do we have? Y equals 0. On the bottom, what do we have? X squared minus 1. Now, we're not quite ready to set the bounds because we have to figure out where do we go between. In other words, we've got to figure out these places. Well, that shouldn't be too bad. That happens when x squared minus 1 intersects with 0. So where are these intersection points occurring for x? Negative 1 and positive 1. So our integral is going to become integral, integral. Our function doesn't change because we're not changing our function. We're not even really changing our integral. We're just changing the description of our region. So it's still the same answer, whatever it turns out to be. All right, working from the outside, where does x go between? Negative 1 to 1. Where does y go from? It goes from the bottom, which is the x squared minus 1, up to the top, which is 0. All right. Well, find the following integral by first changing the order of integration. Now you might say, why bother? Let's just integrate. Okay. How do you integrate e to the y squared? Good, that's the correct answer. You don't. You can't integrate e to the y squared. It's something that we just can't do. We don't have the technology to do it. So we say, okay, well, so there's no answer then, right? Because we just said we couldn't do it. Well, we can't first integrate with respect to y. That's the problem. But remember, we always have a choice. Do we integrate first with respect to y or with respect to x? Could we integrate e to the y squared with respect to x? Yeah, we can very easily. Because e to the y squared would be a constant. So we say, well, look, we can't start by integrating with respect to y, but we could start by integrating with respect to x. But if we wanted to integrate first with respect to x, we'd have to change the order of integration. So this is going to be equal to something e to the y squared dx dy. Now to figure out what that something is, we have to change our bounds. So going a little bit quicker here, x goes from 0 to 4, because that's the outer layer. Y goes from a half x up to 2. So y equals a half x is the sort of a line with a very slow slope of a half. Y equals 2. Looks like that. So here's y equals 2. Y equals a half x. And they happen to intersect very conveniently at 4. So what's our region? Well, our region is it's this triangle. So I'm going from a half x up to 2. So that's our region that we're currently integrating over. And we're still going to integrate over that region. So that's not changing. But what we're going to do is change the way we slice it. So instead of our vertical slices, we're going horizontal. Okay, so we need to describe our bounds. We still have y equals 2. What is this curve on the left-hand side? That corresponds to x equals 0. And y equals a half x. If I write in terms of x, what does it become? 2y. So I now look at my bounds. Well, what's the lowest value of y? Which is down there. 0. I start at 0 and I go up to 2. So my bounds for y, 0 to 2. Well, how about for x? Well, I go from left to right. Left curve is 0, x equals 0. Right curve is 2y. So there's my new bounds. And now we integrate. So we get integral 0 to 2. And we've already said easy integral is just e to the y squared times x. Evaluate from 0 to 2y. And at this point you're probably saying, well, okay, great, you did one integral, but you still have to integrate e to the y squared. But notice what happens when you evaluate from 0 to 2y. What do you get?
2y, e to the y squared.
You're going to get a 2y there. And now you have this extra piece. And that extra piece might be enough to make it work. Because with the 2y, is there an antiderivative of e to the y squared times 2y? There is. What is it? Well, you can use it, but you can also just figure it out. That's e to the y squared. The derivative of e to the y squared would be e to the y squared times the derivative of y squared 2y. You could do a u substitution, but this is good enough. I should have said up here that this is x equals 0, x equals 2y. I got to get into that good habit. Good habits are important. Y equals 0 to y equals 2, giving us an answer of e to the 2 squared, which is e to the 4, minus e to the 0 squared, which is 1. So this is why we like to change the order of integration, because some problems are very difficult in the order that we're given, but by changing the order of integration, we get it to problems which are at least not impossible. And we prefer problems that are at least not impossible. They're much better. Now, when our region is complicated, we may have to break things up into parts, more than one part. So let's consider the following. R is the region where y is less than or equal to x squared, and 0 is less than or equal to x is less than or equal to 2 minus y squared. So I'm not going to hum and haw too much here, because I do want to sketch this. Okay, y is less than or equal to x squared. So I'm going to come here, and I sketch y equals x squared. We want to be less than or equal to x squared, which means we want to be below the parabola. So we're down here, below the parabola. Now we say x is greater than or equal to 0. X equals 0, that's the y-axis, which means we want to be to the right of the y-axis. And x equals 2 minus y squared, what would that look like? X equals 2 minus y squared. It's a sideways parabola opening to the left. So you come here at 2. So that 2 translates to this 2. And then the parabola opens up this way. So this is the parabola x equals 2 minus y squared. Anticipating what's going to happen, I could also say that this is y squared is equal to 2 minus x, which tells me that the top part is y equals the square root of 2 minus x. The bottom part down here is y equals negative square root of 2 minus x. This parabola, that was the y equals x squared, which of course we could also write as x equals square root of y. Over here, this is x equals 0. Now if you put all the pieces together, remember, we want to be below the initial parabola, y equals x squared. We want to be to the right of x equals 0. And we want to be to the left of this other parabola, y squared equals 2 minus x. The region that does it is this shape here. Okay, so that's our region. So there's a couple of things we should figure out. Do we know where this point is? Or could we find it? It's where the curve y equals x squared intersects x equals 2 minus y squared. So we can guess, and probably they gave us a nice point. This turns out to be the point 1, 1. You can check that 1, 1 satisfies both curves, so it's the point of intersection. Down here, where is that point at? Well, you can just actually read it off. That would be x equals 0, so it would be y equals negative square root of 2. So the question is, how do we set up our bounds? Well, we have to make a choice. Which one do you want to do, horizontal or vertical? If we do vertical, we'll come along, and then you'll notice we're being pretty good until we hit this point. What happens after that point? The top curve changes. So if we do it vertically, we'll have to do 2 integrals. Because anytime a bounding curve changes, you've got to break it up. So we're going to do 2 pieces. So we're going to go from, well, this is a dy dx, f of xy. And then there's another one, f of xy, dy dx. So the first integral goes from where we start to where we have to change. So where do we change? Or where do we start, I should guess? So 0 up to 1. Now, the inner layers. Well, where do we go from? Well, we go from the bottom curve, which is y equals minus square root of 2 minus x. So you can see this should be y equals something, up to the top curve, which is x squared. Here we go from where we intersect to our next point, well, 1 to 2, the bottom curve to the top curve as functions of y equals. And quickly, we could have chosen something else. We could have chosen horizontal slicing. But if we choose horizontal slicing, what happens? we switch. So again, we have to make two integrals. So whether we do horizontal or vertical, we're going to do two integrals. So the second version would be what? Well, we still have f of xy, it's just dx dy. So the bottom integral, we start at negative root 2, go to 0, and then we're going from x equals 0 out to x equals 2 minus y squared. Then the second one goes from 0 to 1, because that's where we stop with the y values. We go from the left curve, which is square root of y, to the right curve, which is 2 minus y squared. And so that's how we would put this region in the two different formats. Well, let's do some more problems, because the more problems we do, the easier it gets. And then we want life to be easy. Let R be the region in the first quadrant bounded by x equals 0, y equals 0, and the ellipse 4x squared plus y squared equals 4. Find the integral over that region of x plus 2y dA. Well, that's interesting. All right, well, let's think about that. So we're in the first quadrant, which means that we want x and y to be greater than or equal. So we're in this part right here. So that's the x equals 0, y equals 0. The ellipse, 4x squared plus y squared equals 4. Now, what that means is that if you look at x, how big can x be given that y is not there? And the answer is x can get all the way out to 1. Now, suppose you cover up the x, how big can y be? The answer is you can get all the way up to 2. So it's an ellipse that's stretched a little bit more in the y direction. Okay, so there's our region. So it looks something like that. All right, there we go. So we have this region, and now we want to integrate over this region. So we have to make a choice. And I'm not claiming that any choice is a good choice or a bad choice. So let's think about our curve here. So our curve, that's 4x squared plus y squared equals 4. Now, given a choice, I probably would want to solve for y, because I see it's the simplest to solve for. Y squared is 4 minus 4x squared, or if I take a square root, y is the square root of 4 minus 4x squared, which you can pull a 4 out, that's common, to square root 1 minus x squared. And you're probably looking at that, saying, that's kind of like a circle. It is. It's a circle that's been stretched, because it turns out that ellipses are circles that have been stretched. All right, so, all right, that's not so bad. What can we do? Well, so we solve for this as a function of y, which means we really want to do slicing this way, because we want to go from a y equals to a y equals. So our integral over our region of x plus 2y dA is going to become the same function, x plus 2y. We're not changing the function, we're just doing a better job of describing our region. We're going to have this is going to be a dy dx type integral. And we say, okay, what's true about x? Well, x, that's our outer bounds, that's going from 0 to 1. So we go from 0 to 1. What about y? Well, we're going from the two curves. So we didn't write this down explicitly, but there we do. Now we have it. So we're going from y equals 0 to y equals 2 square root 1 minus x squared. So what do we get? Well, we get integral 0 to 1, integrating with respect to y. We'll get xy plus y squared. And now we're going to evaluate from y equals 0 to y equals 2 square root 1 minus x squared. And doing that, we get 0 to 1. We're going to get x times y. So x times y, that'll be x times 2, so I'll write that as 2x square root 1 minus x squared, and then plus y squared, which is 4 minus 4x squared. Because we actually did y squared over here. It's 4 minus 4x squared. And that integral is going to be dx. Now, that's not so bad. So the square root of 1 minus x squared, that was our bound. We were worried about that, but it turns out because of the x that's there, it's not going to be anything to worry about. Indeed, we can do this integral. Let's really do it in two parts. So let's say we're working on the first part here. What do we see? Well, if we set this inside part to be u, then minus 2x dx would be du. So we could do the following, say that like this integral, let's maybe do it on the side here, integral 2x squared 1 minus x squared dx would become the square root of u, which is u to the 1/2, and then because of the minus, we have a minus du. So that would be minus u to the 3/2 multiplied in front by 2/3. So we get minus 2/3, 1 minus x squared to the 3/2. Okay, so that would be what it would work out to be. So we have over here minus 2/3, 1 minus x squared to the 3/2. Then these parts, not so bad. 4x and minus 4/3 x cubed from x equals 0 to x equals 1. We can plug in 1. If you plug in 1, the first term goes away because you have 1 minus 1. 0. Gone. Gone. Good. Good. All right. Plus 4 minus 4/3. And we're going to subtract, plug in 0. Well, 1 minus 0 would be 0, 1 to 3/2. So it's actually minus 2/3 there. And then those two terms are gone. Plus 0, minus 0. Now, zeros go away. Minus, minus, plus. So we have a minus 4/3 plus 2/3. So that becomes 4 minus 2/3. Well, that's 12/3 minus 2/3 gives a final answer of 10/3. Well, that's kind of nice. In fact, a little bit surprising. We may have thought that maybe there'd be a pi or something because of the shape of our region, but it doesn't have to be. Things can work out. Things can work out very nicely. Ah, the joy of calculus, where everything works out nicely. So, one last problem. Here we go. Suppose we want to evaluate the integral -1 to 0, integral 0 to 1, of cosine y cubed plus y dy dx, plus the integral from 0 to 3, integral square root of x over 3 to 1, cosine of y cubed plus y dy dx. Now, the problem doesn't actually tell us how to do it, so we have to think a little bit and say, okay, well, what's going on here? Well, if we stare at this, we'll start to say, I don't know if I'd want to integrate this function with respect to y, because I don't know how to integrate cosine of y cubed plus y. Now, there's a temptation, and I see this a lot. A lot of people would say, oh, that's not so bad. It's not bad at all. That would just be sine of y cubed plus y, and then divide by the derivative. That's how it works. No. Be smart. Don't start. That's not how it works. It's much more complicated. So this is very sad. If we see those kinds of things, we're very sad. Why? Because it means we're going to lose points. And sometimes it could be a lot of points. And we don't want to lose any points. So keep in mind, we don't ask you to integrate very complicated things. So if you ever see something that's complicated, and when I say complicated, I mean these are the following functions we expect you to know. Cosine, sine, tangent, secant, secant squared, secant tangent. You're like, wow, there's a lot of trig. Yes. In fact, there's more trig than anything else. U to the k, 1 over u, e to the u, and 1 over 1 plus u squared. That's it. If you're not doing one of these functions, then you should not try to integrate. Don't try to be creative. Creativity, it's great for some majors, but not for math. You don't want to be creative. You want to be able to rigorously work through the problem. But we say, okay, we can't integrate with respect to y. It's really not one of these things. But I can integrate that really easily with respect to x. In fact, it's super, super easy to integrate with respect to x. So we say, idea. Our idea, let's change the order of integration. And moreover, let's try to see if we can't merge these two together. So let's understand this. So this is, let's call this integral number 1, and we're going to call this integral number 2, because we're not very good at naming things. So let's look and see what these integrals look like. So what does number 1 say? Number 1 says go from negative 1 to 0 for x, so negative 1 less than or equal to x less than or equal to 0. And then y says go to 0 to 1. 0 less than or equal to y less than or equal to 1. That's pretty easy to spot. That's a little rectangle. So this is integral 1. Is this part right here, this little, in fact it's not even just a rectangle, it's a square. Now, integral 2 says what? Well, 0 less than or equal to x less than or equal to 3. So we're going to go out to 3. So let's say that's 3 there. And then y, we go from square root of x over 3 less than or equal to y less than or equal to 1. Now, what's true? Well, y equals 1. That's easy to draw. How about square root of x over 3? It's like the square root of x, but it's been sort of scaled down. Now, one thing to always try is say, well, what happens at the very furthest point, at 3? You get square root of 1 over 1, which means it's actually going to hit here. At 0, plug it in, you get 0. So it's a square root function that comes up and looks like that. So integral 2 is this piece. All right, so can we say? Well, we can label a couple things. Over here, we have x equals negative 1. Up on top, we have y equals 1. Down here, we have y equals 0. And here, this is the curve y equals the square root of x over 3. But you can rewrite this. Square both sides, move terms around, you get x equals 3y squared. So, now we say, aha, we can do this integral in one pass, one single pass, because previously we were doing integrals where we were slicing this way because of the dy dx. If we change the order of integration, we now slice in the other direction. And so these two separate integrals become one. The nice thing is, previously, if we needed a vertical slicing, we changed our behavior at 0, which is why we had to split the integral at 0. But horizontal slicing, behavior doesn't change. Life is good. So let's see what we have. So we're going to have the integral. The function doesn't change. That hasn't changed. We're just changing the way we describe our region in a different way. It's now dx dy. Where does y go from? Well, I start at y equals 0, and I go up to y equals 1. So 0 to 1. Where does x go from? Well, I start on the left at x equals negative 1, and I go to the right, which is x equals 3y squared. And it should be an x equals. See, the dx says these are x bounds. X equals negative 1, x equals 3y squared. All right, so now we have our integral. Say, all right, let's at least do the first layer, integral 0 to 1. Then we have cosine of y cubed plus y. That's acting like a constant because we integrate with respect to x, times x, evaluate from x equals negative 1 to x equals 3y squared dy. So that becomes integral 0 to 1 cosine y cubed plus y. And now, plug in 3y squared. We have 3y squared, subtract, plug in negative 1. Well, minus 1 makes plus 1 dy. Now I say, wait a second. Look, what do we have? Y cubed plus y See, we couldn't integrate that before, but now we introduced a new piece. If we set that to be u, then this becomes du, which means very integrable. Very, very integrable. So this is going to become the integral cosine of u du. But what are the bounds? When y equals 0, that becomes u equals 0 cubed plus 0, which is 0. When y equals 1, we get 1 cubed plus 1, which is 2. So, the integral of cosine is sine. Sine of u, evaluated from 0 to 2, which is sine of 2 subtract sine of 0. Now sine of 0, that happens to be 0. That's gone. And sine of 2, that happens to be sine of 2. And that's the answer. And life is good. All right. So there's a lot of power that comes from changing the way we do the integral. We're still doing the same problem, but by changing our order, we can make progress. But of course, maybe there's more than just changing order. Maybe we can change even the way we describe our locations, different coordinate systems. And that is what we're going to be talking about next time. That's it for today. See you later.